We're going to go over molecular geometries for the case where the steric number is equal to 6. An example of this would be the molecule sulfur hexafluoride. The Lewis structure for sulfur hexafluoride is going to look like this. If we were to calculate the steric number for sulfur in sulfur hexafluoride, the steric number, that's going to be the number of atoms attached to the sulfur, which is 1, 2, 3, 4, 5, 6, plus the number of lone pair electrons on the central sulfur, which is 0. Of course, that's going to give us a steric number of 6. When there's a steric number of 6, the pairs of electrons surrounding the central atom take on what's known as an octahedral arrangement. This model here is representative of the way that the bond pairs and the terminal atoms organize themselves in sulfur hexafluoride in an octahedral arrangement. We see that the terminal fluorine atoms on the central sulfur orient at the faces of a cube or the corners of an octahedron. In an octahedron, all terminal atom, central atom, terminal atom bond angles are 90 degrees, and it's easiest to see that in this plane right here. There's a we'll call it an axial atom, even though all positions are identical. We're just going to call this one axial, and the one down here on the bottom axial. So those are I'm holding them in my hands. And then there's a plane of 4 atoms that cuts right through here. This atom, this atom, this atom, and this atom. If we look at these 4 atoms, it's easy to see that the terminal atom, central atom, terminal atom bond angles are all 90 degrees. All of these are right angles. And it doesn't matter which way I turn the structure, we end up seeing the same orientation of all atoms. And that's because all of these terminal atom positions are identical to one another. All bond angles end up being 90 degrees to one another in this octahedral arrangement. Now there are other molecules that can give us an octahedral arrangement. For example, xenon oxytetrafluoride. The Lewis structure for this molecule looks as follows. Where we note that in addition to the atoms attached to the central xenon, there's also a lone pair. So if we were to calculate the steric number for xenon oxytetrafluoride, we're going to take the number of atoms attached, which is 1, 2, 3, 4, 5, and then we'll add in 1 for the lone pair. That's a steric number of 6. In this case, we're going to remove one of the connections to an atom and replace it with a lone pair. We still have an octahedral arrangement of the electron pairs surrounding the central atom. They all still take on this octahedral orientation, but in this case, one of the bond pairs is replaced with a lone pair. We still essentially have a 90-degree angle between the bonds, but we're going to remember again that this lone pair is going to exert a little more pressure on the bond pairs, and that's going to squeeze these bonds in a little tighter. And so the bond angles here are going to be slightly less than 90 degrees. Now, if we want to describe the molecular structure of xenon oxytetrafluoride, remember we're going to ignore the lone pair and just kind of look at the structure that's left. These 4 atoms here and the central xenon are all going to lie pretty much in the same plane. Keep in mind there's a little bit of bend to these 4 molecules. And then this particular molecule up here is sitting up above the plane of the other 5 atoms that are in this plane of my hand right now. So this is sitting up above. If we imagine drawing a line from each terminal atom up to this top atom, this looks like the apex of a pyramid, and the base of the pyramid represented by the 4 atoms that I'm rotating, the base is square. And so we would call this molecular geometry square pyramidal. So while the electron geometry is octahedral, if we consider all of the electron pairs, including the lone pair, if we just look at the molecular geometry, which is the relationship of the atoms to one another, we would call this molecular geometry square pyramidal. Of course, keeping in mind that these 4 atoms in this region are bent up a little bit. They're not quite going to be 90 degrees. They're going to be bent in a little bit from the presence of this lone pair that exerts a little more pressure on the bond pairs. Finally, we'll look at the case of xenon tetrafluoride. The Lewis structure of xenon tetrafluoride looks like this. If we were to find the steric number for xenon tetrafluoride, steric number, that's going to be the number of atoms attached to our xenon, which is 1, 2, 3, 4, plus the number of lone pairs, which is 2. That gives us a steric number of 6. The way the lone pairs and the bond pairs orient themselves in xenon tetrafluoride is like this, where what's done is the bond pairs occupy opposite positions of 4 atoms that are going to lie in the same plane. And that's done because these lone pairs exert, remember, greater repulsive forces for each other than they do, they exert greater repulsive forces than do the bond pairs. And so we want to get these things as far away from each other as possible. The best way to do that is to stick them at opposite sides. If we did something like this, then those lone pairs would be quite close to each other. We can maximize the distance between the lone pairs by setting them at opposite sides of this particular plane. Now here, what ends up happening if we want to describe the shape of this molecule is we're just going to remove the 2 lone pairs, and we see kind of that what we're left with is a square. And we call this a square planar molecular structure because all these atoms lie in the same plane. So we call this square planar. So an octahedral electronic geometry that has 4 atoms and 2 lone pairs takes on a square planar molecular geometry, and in this case, the bond angles remain 90 degrees. That's because the lone pairs, while they do exert repulsive forces, of course, on these bond pairs, they do so equally in both directions. And that means that the distortion balances out in both directions, and we really do end up with a true square planar molecule.